Okay, thanks for staying around. I know it's near the end of the day, so I'll promise I'll be quick for this one. So this is a continuation of the performance study that I've done for the HPC Advisory Council, similar to the one that I talked about yesterday. So today I'm going to talk about a different application that's called Pam Crash, or the ESI VPS, Virtual Performance Solutions. So I'm just going to dive right to it. In case that anybody might have interest in other HPC applications, we always have a list of them online. The URL for the web pages actually appear at the bottom of the page. So if you have time, feel free to check them out. So we have 130 user applications posted there. Some of them are commercial applications, some of them are ISV codes, like open source codes. So just another brief overview of what we have at the Advisory Council Cluster Center. So we have many generations of hardware that are out there in the lab. The lab is actually located in Sunnyvale, California, in the US. We have Haswell Systems, the latest one from the Dell and HP. Thanks for those vendors for providing us the resources for running such a benchmark that we're doing. We also have previous generations of the clusters such as Ivy Bridge and from Intel, and also the Abu Dhabi from AMD and some other architecture as well. So we have GPU clusters, and as well as the cluster-based, InfiniBand-based cluster storage that we can run our benchmark on. Similar to yesterday, we have an overview of the things we're going to go over. So first, I'm going to have describe to you some of the ways that I do profile and optimize HPC applications. So today, since I'm actually going over an ISV code, and I will not have the opportunity to actually tune in compiler, so I'm just going to be focusing on other areas instead. At the end, I will do a quick summary of my findings. So again, similar to what I have shown you yesterday, in order to achieve a really good HPC performance on the workload, you kind of want to go into the area where the user application spends the most time on. So by doing an MPI profile, or by doing a profile on the user application, you kind of get a sense on how much of the time that it's actually spent on compute, in I/O, or in network. So, and then we're focusing on the largest percentage time for that particular area, and try to find a better runtime and things like that. So, some of the ways that, or some of the tools and profilers or tools that I use are listed here. In case any one of you are interested, these are very well known. So it's that you can get it from the web. So I'm pretty sure that some of you may have known them already. As I said, today we're going to go over the ESI performance, the virtual performance solutions, previously known as the Pam Crash. This is a study that's done jointly with Dell and Intel, as well as Mellanox. And we're here to show the performance, and also some of the MPI libraries tuning parameters as well. And in general, the way to increase performance for VPS or Pam Crash. So Pam Crash, you may have heard of from before. So Pam Crash is developed by the ESI group. It is used for crash simulations, such as other CFD applications that are out there. It's primarily used in the auto industry for simulating car crashes in other areas in that region area. I'm going to skip this one. So here, I'm describing to you the hardware configuration that I use for my system. So for this particular one, I work on the Intel Ivy Bridge cluster. Some of the the details are shown here, such as the MPI libraries that ESI group actually supports. So, for instance, they support running with platform MPI. However, the MPI that I actually use for OpenMPI is a little different from the ones given here, which I'm going to show you a little bit later about why, in order to get the better performance. So, and it's also as a way for me to run with the Mellanox HPCX library. So these actually have some tuning parameters for increasing the performance for this workload. For the benchmark input data, using the Neon Fine car-to-car crash, which is like Chrysler Neon running at 56 kilometers per hour at 120 milliseconds single precision. Unless otherwise stated, so there will be another comparison that I'll be doing for something else. So let me first describe to you the first test I run for the Pam Crash, for the ESI VPS performance solution. For this particular way of running it, I'm actually using a way of doing the hybrid mode again. So since ESI actually has a way of running the hybrid, meaning that you're mixing the OpenMPI process and spawns threads for the number of cores actually available on the system on the processor. So by spawning one OpenMP threads, meaning that I actually have 20 CPU cores per node. So I basically run 20 CPU cores and 1 threads per process. First is for the case that I have 2 OpenMP threads. It basically means that I have 10 processes that's run per node, and each of them spawns 2 threads. So the second case is actually save us a little bit more time, and you see that the increase in performance by a little bit. So I kind of assume that if you actually do get to use the threading a little bit more, you'll probably see a little bit more or better performance. So at 32 node, we actually see the scalability increase, by 8%. And the difference is actually not as noticeable for the lower core count. So maybe it's for this particular input data that we are not actually seeing as much of the performance difference. But as you either scale out to more and more systems, or you use actually more OpenMP threads, I tend to expect that you actually get a little bit better performance. So similarly, when we actually do that for using just MPI mode for this one, and I compare with different interconnect, the subsequent slide after this is going to be using the hybrid mode and compare with the different network interconnect. So this one is the MPI mode only, so which means I'm running 20 processes per node. And here you can actually see that how well the interconnect will scale. So surprisingly, Ethernet do scale up to 8 or 16 node for this particular input. I wasn't able to run the 16 node for 1 gig E, but that's why I kind of skip it right here. So what you actually can see that 1 gig E actually was stop scaling around 4 nodes or so, which is actually pretty good. And we're actually going to show you why is that, because by actually reading the MPI profile later on. In the subsequent slide, I'm going to show you. But the performance differences actually start to diverge. So after 16 node, you see very clear difference about InfiniBand versus Ethernet or 10 gig E. So 10 gig E is actually an okay solution when you're actually up to 8 nodes or so. So this is so this is a really interesting finding, because sometimes for other workloads, such as Quantum Espresso from yesterday, it doesn't really get up to 4 nodes. So, and the reason of that is actually shown up in the subsequent slide in MPI profiling. Well, not this one, but the one after this probably. So in this comparison right here, what I'm showing you is that the hybrid mode, we have 10 MPI processes. Each of them spawns 2 threads. So similar to the previous slide, that we actually see a really big difference and huge gain from InfiniBand versus 10 gig E at 32 nodes. But if you compare the difference is actually closing in. Instead of 7 times worse for 1 gig E, you actually it's a little bit less worse for 1 gig E. For 10 gig E, it's actually worse, but it's actually doesn't show as much of the difference anyway. You're losing performance at that scale at 32 nodes. So in here, this will show you how much of the time actually spent in communication versus the actual workload in the user time, which is the computation. So the one in red is the time that's the overhead, the MPI overhead that each one of those interconnect actually spent. The 1 gig E spends the most time in communication. You see that a big, overview over almost all the time actually spent on the MPI communication. So which is really not really a good choice when you actually run it at a large scale. InfiniBand on the other side, is using the IDMA technology, so that's why it actually bypasses the CPU involvement, so the CPU actually can do actual workload. So on the other hand, it actually spends much less time, a third of the time in communication. So it's actually able to spend more percentage of time actually in computation. So 10 gig E is halfway in between. It's really not as good as InfiniBand. Meanwhile, you actually do have, I think like 4 or 5 times more time in computation if we're taking into consideration of the overall runtime. So this shows you about the communication time in MPI. Where are they spent on for this particular application? So majority of the time for the VPS or Pam Crash is actually occurred in all reduce. So you'll see that this graph right here, it shows that a majority of the time actually spent on the red color, so which is all reduced. And what you notice is that they're not very even out. What actually that means is that a lot of the time the processes actually doesn't come into the same place when they do the collective operations. So what it actually means is that like some processes actually spend more time in the collective operations, some actually spend less. That actually reflects the load imbalances. What's that mean about load imbalances? So take it for instance, right? When you have car crash simulations, so they either do a mesh or for the domains, and then each one of the MPI process in charge of part of a domain, and they calculate for a particular part of that car or part of the impact from the whatever that is trying to hit. Some part of it is actually spend more time in computation or communication. So a lot of it actually has to do with that. So because some processes actually take on more workload, some actually take on less workload. That's why you actually see the imbalance like this. And sometimes you cannot avoid it. Sometimes that you can actually change it by rearranging the processes or changing something about the way that you partition the domain for the input data. If you have the luxury of doing that, this is a way to work around it. Essentially, ideally, you actually do want to they all kind of come into sync and to be as close to an even slope as possible. But unfortunately, in a real case, it's not always happening like that. So this kind of explains to you about what we're actually seeing here. But it's okay. Even though that we don't have all around in the sync, you do see that majority of the time actually, that's spent on all reduced, and it's actually, it takes about 24% of the overall runtime for that particular MPI operation. Later on, I'm going to show you what are the ways to kind of optimize that kind of workload, because collective operations is really hard to tune sometimes. Taking the previous slides, and then we actually running the same thing, the same MPI profile for 1 gig E and 10 gig E. So you see that the pattern is pretty much the same, like the previous slides. The only thing that's different is the scale of the y-axis, which actually represents the time in seconds. So, which is no secret, 1 gig you actually spend a little bit, much more time in the cloud heap operation, because there are too many. As soon as you get to the 32 nodes, there are so many traffic on the network actually causes it to have a traffic jam. So they wasn't really productive in a way to, Ethernet was really not productive in a way to help on this kind of communication. And 10 gig E helped a little bit better, but still much higher time span for all reduced compared to FDR, which is happening on the previous slide. So, as I told you earlier, I probably have shown you this slide from yesterday on the Quantum Express. So sometimes I do get questions about how do I create a MPI communication profile. So I'm showing you right here. This is the tool I use sometimes. So one of them is called IPM, the Integrated Monitoring Profiling tool. So you can actually download it and compile it. And if you do actually use a different MPI, you do have to recompile for different MPI because it's actually making use of the profiling interface in MPI standard. It's called PMPI. So it's different between different releases of the MPI library. So if you do have, like, let's say Intel MPI or OpenMPI, you kind of do want to recompile. It's not just it's not something that you just build one and then and just work. But the good thing about it is that when you actually, for me actually, if I actually do want to get profiler on for, let's say, ISV code, I actually don't have the luxury of taking the code and recompile with profiler because I don't have the code. They only get the executable from the software vendor. This is a really good tool because it actually allows me to do a preload of the share object. So I don't really need to compile the profiler with it. I could just like preload it with it and then run with it. And at the end of the run, I will get an XML file that generates some statistical data for me to generate the web page that shows you all this, all these graphs with a lot of information, such as the one that's shown up right here. So, as I mentioned to you briefly earlier, during the configuration page, VPS or Pam Crash does supports like other MPI implementation or MPI library, because I actually do want to see the difference on the performance side between different libraries, right? So, however, unfortunately, the ones that actually are included in ESI Pam Crash or VPS does not make use of the latest OpenMPI. So it has the support for platform MPI and OpenMPI. The OpenMPI executable, the Pam Crash executable for OpenMPI is actually comes at a much older version. It actually supports OpenMPI 1.4. So there are little tricks that I actually did to make it work. So I'm kind of documenting here. Hopefully it will be kind of interesting if you do want to try it out. For testing the performance difference. And for my case, I actually did see some performance difference between the, using OpenMPI versus a more tuned version of OpenMPI called HPCX and platform MPI. So for me, it's actually getting interesting to try it. So I'm actually sharing you the steps here in case you do want to follow. It kind of involves like adding some links and share soft links to actually make some of the share objects that's not available in the latest OpenMPI to work. So if you do want to get to try it, so here goes the instructions, and I do actually have another more appropriate write-up at this location right here at the bottom of the page. If you do want to take a look, feel free to check out the web page. And actually, HPC Works web page, we do have installation instructions for other non-commercial or open source applications. So we're in the process of reviewing and refreshing the content so that it will be very updated to the current system architecture. Because as you know, newer system architecture like Haswell comes with their own new compiler flags, like such or instruction sets, such as for the AVX2 instructions and other things like that. So we are in the middle of refreshing all those like installation instructions. So as I told you earlier, there's actually a feature in OpenMPI to support something called FCA. FCA stands for Fabric Collective Operation. Fabric Collective Acceleration. So it actually supposed to offload and speed up the MPI collective operations. So MPI collective operations, such as some of them actually are, they involve many of the user processes or MPI processes to actually communicate all at the same time. So this is a really costly communication in MPI. So for the FCA, it allows you to offload that kind of communication onto the network, and the user process the CPU actually would not need to spend that much of a time actually doing processing that kind of operations. So by applying FCA in OpenMPI, we actually do see that there are quite a lot of improvement at the larger scale. Well, 9% is actually pretty good, I think, because when you look at the amount of time that actually, in the previous slides when we're doing the profiling, the all-to-all actually spend, I think 27% or 24% of the overall runtime. It actually means that there are 24% of the performance that it could be improved of the overall runtime. So we see about 9% actually being shown up as the time that's been saved. So at least we get some of the time back, some of the performance improvement back. Besides the enabling the FCA parameters that's shown up on the top line, there's also some other some information that actually in FCA I actually do have to set it to make it more to make it work. So I'm also documenting here in case any one of you do want to see and try it out. For this particular slide, so we're comparing the platform MPI versus the improved version of OpenMPI. That's with the FCA support. And what we can see here is that for platform MPI, using the out-of-the-box settings, which does processor binding plus something that's already been used for them to support running Pam Crash, I'm seeing that we get 10% of performance improvement over that for the 32-node case. So I think it's actually kind of validates about the performance improvement in FCA and in OpenMPI. It's able to show that with those kind of like tuning parameter, we're able to see better performance. That actually kind of validates what we actually doing that. Here comes the part that we're comparing whether or not we get more benefit by using turbo mode or not. So, and at what cost actually? Because enabling turbo mode does have a cost for doing that, because it actually spends more power for enabling that. And here we're actually showing you that it seems like regardless of how many machines that we use, the improvement for enabling turbo mode is always consistent somehow. Somehow I always get like 8% of the performance improvement, but at the cost of around 11% of additional power being used. So here's an interesting result that we're able to get it. There's something called the MSR tool, which I think that's what I use in order to adjust the turbo mode like dynamically without having to reboot the system on all the nodes. So once I have the turbo mode enabled in the BIOS, I use this tool to actually just turn it off and on throughout my runs. So if you do actually wanted to try, this one of the tools that's available. I think it's open source. course, like the hardware OEMs that I work with on this one, which is Dell, they do have the sysconfig tool, which you can actually modify the BIOS settings in the OS. So, and then all you need to do is to reboot the system, and it will make the changes automatically after the reboot. So in case you are wondering how to do it, here's the way to do it on a Dell platform. Another interesting comparison for different CPU frequency, this one is we're comparing a 2.0 gigahertz versus 2.7 and a 2.8 gigahertz, and another 2.8 gigahertz with a turbo mode on. So we do actually see quite a big, I would say, big savings and a big, decline performance by. Actually, on the right-hand side, you get an additional comparison, which is running at the 1.2 gigahertz, which nobody actually uses, but for kicks, I just do it. Much worse performance at 1.2 gigahertz. But surprisingly, not a really huge difference at 2.0 gigahertz. Consider the big, decline in not such a big decline in the CPU frequency. The default is always 2.8 gigahertz with turbo mode on. That's my baseline. So that's what you see on the on the right hand side, darkest bar on the right hand side. That's my supposedly the default, the normal case that I've been running for all these cases throughout my slides. So I'm doing the rest of the different CPU frequency only for this slide right here. So this is what I'm comparing. So for example, we're actually seeing quite a big decline performance at 2.0 gigahertz, and the savings of that is actually huge as well at the same time. So if you do get to try it, you'll probably see pretty much the same thing. This particular slide shows that the difference in performance when running with the single precision versus double precision. In a lot of the scientific calculation, double precision is being used, but as for the for an interesting comparison, I was actually running it just to show how much of the time that you actually can save by running single precision, which doesn't really mean that you should run single precision, but it just means that like how they how much of the time can be that running a double precision actually can cost you. So as you can see that at higher node count, the percentage difference is also gets widened. So in my belief is that when you have more and more systems running, and you actually have more and more data that needs to pass along on the network for the double precision side of it. So therefore, you see the gap is actually widened. So this is my my speculation. Just a few words about the IO from IO profiling. So we see that there are some IO that's happened throughout the run. This is a synthetic benchmark. Well, I'm going to say synthetic benchmark, but it's more like a workload that doesn't do too much of the output. Because typically for simulations like this, either throughout or at the end of the job run, you would actually get a really big dump on the output file. For this particular one, obviously it seems like the dump of the result is actually disabled. So that's why you actually don't see that much of the output at the end or throughout the run. But in the middle of during the run, I'm actually separating out the rank 0 node versus the rest of the node. So you see the difference is not as clear, and they're pretty much the same on both sides. So it does some periodic rise throughout the run, but I would not say this actually depicts the real application when you're actually running Pam Crash. But this is a good indication that that there are some I/O in this application. I think I've gone over something like this from yesterday about how to read this chart. So this is an MPI profiler output from IPM. So the ones that actually we're interested in, as we mentioned earlier, is to find out which one of the calls actually spend the most time in MPI. Previously, we have talked about it was all reduced. So we just look for the one that says all reduced with the bright red, and trying to find out what kind of the messages it actually happens on. So for the all reduced, we see that it's around somewhere right here. I think it's between 4 bytes and about 224 bytes, which is, I think it's this line right here. This actually shows us that, what message size is actually all reduced actually being used. So when you go back to the Ethernet performance, and you try to understand why Ethernet would not scale to versus InfiniBand, this is one of the things that you also can kind of correlate to. Maybe Ethernet's performance is for all reduced is not as good for these message sizes or some other network interconnect, right? So you can kind of draw some conclusion like that. This is like basically it shows a spectrum of the messages for that you get for different node sizes, node counts. So we have 1 node, 2 node, 4 node, 8, and 16. So they are pretty much the same. They fall in pretty much the same range. I would not say too much of anything else about this because they're pretty self-explanatory. This to show about how much of the data that's being passed around the network. So on this case, we have 1 node, 2 node, and 4 and 8. So they kind of pretty much stay around the same range of the data that should be passed around, regardless of how much of the nodes they're involved. So I mean, each one of the ranks should take part of this. So if you have more and more systems, you'll get pretty much a duplicate of this for the next few sets of nodes. So the amount of data is going to be repeated, so you'll get twice as much of the network traffic if you have more and more systems. This, as I said earlier, just now, so when you kind of double the number of nodes, you do get quite a lot more, pretty much double the number of traffic going on the network. So this may be kind of why other network interconnect may not be handled that much of the traffic. So let me skip this one. So I think as a summary, so what I actually want to show you is what I just talked about. So the hybrid mode in the VPS or Pam Crash actually helped a lot. If you actually do get to try to run with more threads and less MPI cores, I believe that you do see more and more difference, and better performance by doing that. InfiniBand helped a lot versus other network interconnect, so it's able to allow you to scale to 32 nodes or maybe more, and also. As far as the MPI library tuning, we're able to demonstrate that FCA is able to offload some part of collectives. So out of the 24% of the time spent on all reduced, we're able to get about like 8% better performance by applying FCA. So OpenMPI sometimes actually do outperform other commercial MPI. If you do understand kind of where it's actually spend their time on and try to attack it. So so the last point is probably about the collective operations actually being used kind of exclusively for MPI about this application. So which is what we just talked about. Other than that, that's all I wanted to say. Thank you very much.